Hi friends, here in this video we are going to see a problem on vapor power cycle. So let's get started. Now here is the question given. It is said that steam working on Rankine cycle is supplied with dry saturated steam at 25 bar and exhaust takes place at 0.2 bar for a steam flow rate of 10 kg per second. Now whatever these data are given, I'll explain them with the help of the layout of this steam power plant. So at first, now this is the general layout of a steam power plant in which there are four major components: boiler, turbine, condenser and feed pump. Now in the boiler, water would be heated, it gets converted into steam. That steam will pass through the turbine, and then in that turbine the steam is going to expand. That is, here at the inlet the enthalpy would be H1. So there would be a drop in enthalpy from H1 to H2, and at the same time we are going to get the work, which is the shaft work of the turbine due to the rotation of the shaft. Then after that, at point number 2, the steam is coming out from the turbine, or we can say the exhaust steam. It goes into the condenser where the phase transformation takes place. It means exhaust steam is going to enter the condenser, and when it leaves the condenser at point 3, it will be a saturated liquid, or we can say water, and that water would be pumped with the help of the feed pump back into the boiler. Again the heat is supplied in the boiler, the water gets converted into steam, and the cycle goes on. In the condenser, cooling water is getting circulated. So whatever the exhaust steam is there, it comes in contact with these pipes in which the cooling water is circulated. So the steam gives away the heat to the cooling water, and the temperature of the water will rise. At the same time, the phase transformation is taking place from point 2 to 3, and at point number 2 we have the exhaust steam at the exit, and that exhaust steam will be converted into saturated liquid inside the condenser. Now the data which they have given, I'll show that data on this thermal power plant layout. So steam is working on Rankine cycle, supplied with dry saturated steam at 25 bar. So the steam is supplied by the boiler, and it is dry saturated given. So it means the steam is 100% dry. Pressure is 25 bar. So at point number 1, steam is having 25 bar pressure, and since it is mentioned that the steam is dry saturated, so the dryness fraction of the steam at point number 1 will be equal to 1, because the steam is completely dry. If it would have been a wet steam, then the dryness fraction would have been less than 1. Next, and the exhaust takes place at 0.2 bar for a steam flow rate of 10 kg per second. Exhaust pressure is given and mass flow rate of steam is given. Exhaust pressure P2 0.2 bar, and the mass flow rate of steam, which is m dot, it is given by 10 kg per second. Then the question is, we have to find out the quality of steam at the end of expansion from the turbine. So at the end of the expansion, that is at point number 2, we have to find the quality of steam. So whenever the quality of steam is given, steam are of 3 types: wet steam, dry steam and superheated steam. So if at the turbine inlet the steam is dry, at the exit it would be wet steam. So we have to find the quality by finding the dryness fraction of that steam. So we have to basically find out x2 over here, that is the dryness fraction, because that would be indicating the quality of steam at the exhaust from the turbine. Next, we have to find shaft work. So shaft work is the work which is produced by the turbine. Next, we have to find the power required to drive the pump. Feed pump is a work consuming device, so the power which is consumed by the feed pump is what we have to find out. Next, we have to calculate the work ratio. I'll denote it by capital W and R, so work ratio. And at the last, we have to find the Rankine efficiency of this power plant. So this is the initial setup of the problem. Now to start the problem, I'll explain whenever we are solving the problem related to vapor power cycle, or we can say the steam power plant, we have to try to get all the enthalpy values. So here there are 4 major points, 1, 2, 3 and 4. So we have to find out all the enthalpy values at all these 4 locations, and then only we can go for the further part of the problem. Now how to get that? For that I am writing an important hint here into the solution part. So here the hint is get H1 and H2. Now what are H1 H2? H1 is the enthalpy of the steam which is leaving the boiler or entering the turbine. H2 is the enthalpy of the steam which is coming out from the turbine, or we can say the exhaust steam. So both the enthalpies we have to get from the Mollier chart first. Next is get H3 from steam table. H3 is the enthalpy of the saturated liquid which is coming out from the condenser, and next we have to get it from the steam table, and get H4 from special formula. Now what is this special formula? For that you will have to watch this video till the end so that we can understand how to calculate the value of H4. Now since we know from where to get all the enthalpies, first I would be drawing the HS diagram because that is needed in the problem. This HS diagram is the enthalpy entropy diagram. Enthalpy would be in terms of kilojoule per kg, entropy kilojoule per kg Kelvin. Now that diagram will look like the curve. It is in this way. It is the saturation curve. So the dryness fraction of this curve is 1. Steam is completely dry. And now after that we have to show the pressure variation. So these are the pressure lines. Now here is the boiler pressure. This is the condenser pressure. So the system operates between 2 pressure limits, boiler pressure and condenser pressure. Boiler pressure will be denoted by P1 and condenser pressure by P2. And this HS chart is nothing but that is the Mollier chart. Now since they have mentioned that steam is dry saturated at the entry, so this curve shows the dry line. At the same time, whatever is there behind this curve, this region is called as the superheated region. Now here the steam is not superheated, it is just dry saturated. So with the boiler pressure intersecting this curve, I get point number 1. Now assuming that the expansion in the turbine is isentropic, so this would be a vertical line showing the isentropic expansion in the turbine. Then at point number 2 it is leaving the turbine and entering the condenser. At the condenser it gets converted into saturated liquid. So this curve, onto the right hand side we have saturated vapor, and onto the left hand side, because this is the critical point where the phase transformation takes place, so this left curve is the saturated liquid curve. So from 2, following the same pressure line, we reach up to point 3, that is the saturated liquid region, that is the liquid which is after the condenser or the condensate. Then after that at 3 it is entering the feed pump, and in the pump we are assuming that it is isentropic pumping or isentropic compression from condenser pressure at point 3 to boiler pressure. at point 4 because P1 and P4 are same. Then from 4 to 1 is the heat supplied in the boiler. So this is the complete cycle. Here entropy S1 equal to S2, S3 is equal to S4, isentropic process. Now Mollier chart is just above this critical point. It means whatever the Mollier chart which we are having, it is made, it doesn't have a saturated liquid region, but it has a saturated vapor region and above. So from the Mollier chart, as I have written the important hint here, we have to get H1 H2 from the Mollier chart, H3 will be there from the steam table, and H4 by using the special formula which I am going to explain. So now starting with the Mollier chart for point number 1 and 2, remember that at point 1 the boiler pressure is 25 bar. At point number 2 the pressure is 0.2 bar, condenser pressure. So how to plot 1 and 2 onto the Mollier chart, that I am going to explain. And here at point number 2 we have to even find the dryness fraction. So how to start with the Mollier chart? Now here I have a Mollier chart and I am going to explain how to plot H1 and H2 over it. At first they have mentioned that pressure P1 is 25 bar and the steam is completely dry. So this is the Mollier chart. Here we can see that this dark curve or the dark line is the saturation line. It means the dryness fraction of this line will be X equal to 1, and whatever the region is there beyond this curve, that is the superheated region, and whatever the region is there inside this curve, that is the wet region. And now first indicating the pressure, see these are the pressure lines. If we can see here, starting from 0.01 bar, 0.02, 03 and so on, we have the pressures on this saturation curve. At the same time these same pressure lines are being extended to the top. As we can see here, we have 1000 bar pressure, 800, 600 and so on. So these are the pressure lines. Intersecting the pressure lines are the temperature lines. As we can see here, these are the temperature lines. Now in this problem the temperature is not given, pressure is given, and that pressure is 25 bar. So what I'll do on the saturation curve, here is the pressure which is of 25 bar, and this would indicate point number 1 because it is on the dry line, the dry saturated line. So I have got point number 1 over here. I am marking this. This is point number 1. Then I have to bring this line down like I have shown in the HS diagram, and it should intersect the pressure of 0.2 bar, and that 0.2 bar pressure is over here. We can see it is 0.2 bar pressure. So this line would be extended and we have to drop a vertical line from here where it intersects the 0.2 bar pressure line. That would be point number 2. So for that I have to keep a scale over here and draw a light line dropping vertically up to a pressure of 0.2 bar. So here we have 0.2 bar pressure. So here I am getting the second point. And this drop in enthalpy, that is from H1 to H2, indicated with the help of an arrow. This is indicating the expansion in the turbine. Now I have to get H1 and H2 values. So simply project these points horizontally, because on the horizontal scale here we can see there are specific enthalpy given. Unit is kilojoule per kg. So I have to just project H1 and H2 up to these marking. So what I am doing here is projecting H1, that is point number 1. Now when point 1 is projected, I am getting the value as 2800 kilojoule per kg. So that is the enthalpy of point number 1. Similarly for point 2. Now if you are getting the value anywhere in between, remember, like for example from 2000 to 2100, there is a difference of 100 and each box indicates an enthalpy of 10 kilojoule per kg. So when I am projecting this point, This will indicate the enthalpy of the second point, and my answer is it is 2060 because from 2000 these are 6 boxes above, so I'm getting H2 value as 2060. That value I'm going to write here. So H2 value is 2060 kilojoule per kg, and remember this is a graphical method, so the answers may vary. There are chances of errors as well, so the allowance is plus or minus 10%. It means whatever the answer which I am getting, so there may be a difference of plus or minus 10 kilojoule per kg. So that we have to remember, because this is the graphical method, so there may be chances of the answers not matching, but plus or minus 10% error is allowed. Now after getting the value of H2 over here, I can also find the dryness fraction. See, these are the curves which are showing the dryness fraction. As we can see here, 0.75, 0.80, 0.85, 0.9, 0.95, finally x equal to 1. So these curves which are parallel to the saturation curve, these are showing the dryness fraction. Now I want the dryness fraction of point number 2. So I can easily see that after 0.75, here we have 0.76 and 0.77. So this point 2 is exactly passing through this dryness fraction line, which is of 0.77. So finally H2 value is 0.77. From the Mollier chart, H1, H2 values I have noted, and similarly X2 is 0.77. So the first question I found out, that was we have to see the quality of steam at the exhaust. So X2 has been found out. I can say that this is the first answer, answer 1, and therefore I can comment on this that the steam is wet after exhaust from turbine. Now from the important hint, H1, H2 has been found out from the Mollier chart, even X2. Now H3 I have to get it from the steam table, and remember, to find H3 we know the pressure is 0.2 bar, and we have to look into the steam table for HF value, because on this curve whatever the right hand side values are there, they represent saturated vapor, that is Hg values, that are the enthalpy of the dry vapor, and onto the left hand side whatever the values we are going to get, those are called as HF values, the enthalpy of liquid, or we can say the enthalpy of water over here. Now how to get it? So in the steam table, now here I have a steam table. In that, the first table is the temperature table. So don't go to the temperature table because here pressure is given. So the second table is the pressure table. So on this second table, into the pressure table, we have absolute pressure in bar, and the pressure here is 0.2 bar. So on 0.2, get the HF value. So here is the pressure which is corresponding to 0.2 bar, and in that look for HF value. Here I have HF value, and that HF value is 251.5. 0.2 bar pressure, look for the HF value for the enthalpy of liquid, which is saturated liquid. So I can say that after reaching up till here, therefore from steam table, H3 is equal to HF value at point number 3, and that is at a pressure of 0.2 bar, pressure of 0.2. Also we can say the same would be the pressure of 0.3 because the condensation takes place at constant pressure, and now the value was 251.5 kilojoule per kg. Then after getting H3, now to calculate H4 I am going to use that special formula which I had mentioned, and therefore I'll say that for H4, using special formula, and that special formula is of the pump work. Now the pump is operating between the enthalpies, as we can see here, of H3 and H4. So it would be H4 minus H3, the higher value minus the lower value. So we have H4 minus H3, and the formula is, which we have to remember, that is the boiler pressure minus the condenser pressure divided by 10. And at the same time, so this is the special formula where P1 is the boiler pressure and P2 is the condenser pressure. These pressures need to be in terms of bar by using this formula. So therefore, I can just go on putting the values. H4 is what we have to find out. H3 is there from the steam table. Pressure P1 is 25 bar. P2 is 0.2 divided by 10. So this is the special formula, and from this H4 value can be calculated. It will come out to be 253.98 kilojoule per kg. Now once H4 value is also known, I can say that all four enthalpies have been calculated. And remember, when we are using this special formula, if suppose in any of the problem the pump work is neglected or it is given as 0, then H4 will be equal to H3, because this is 0, so minus H3 comes on the other side. So H4 would be equal to H3 in that case where the pump work is 0. But since nothing is mentioned about the pump work over here, we have used the special formula. Now after getting all the enthalpies, we can find whatever has been asked. So starting with the turbine shaft work. Now turbine work, suppose I am writing it in the small form, that is small w. It indicates the enthalpy in terms of kilojoule per kg, and the formula would be H1 minus H2 unit kilojoule per kg. And why we are getting H1 minus H2? Because whatever is the enthalpy drop in the turbine, that is the amount of work produced. So it is H1 minus H2. And when I write the same formula multiplying with the mass flow rate, I am going to get the power. So therefore Wt, or the power which is produced by the turbine, will be m dot, since the mass flow rate of steam is given, into H1 minus H2, and the unit will be m dot is in terms of kg per second into H1 minus H2, it is kilojoule per kg specific enthalpy. From the numerator and denominator, kg will get cancelled out, so kilojoule per second is equal to kilowatts. So the unit which I am going to get here for the turbine shaft work is in terms of kilowatt. Now putting the values over here, m dot was given to us, it was 10 kg per second. H1 value found out from the Mollier chart, that was 2800, minus H2 value 2060. So therefore the turbine shaft work or the turbine power developed comes out to be, it is 7400 kilowatts. So that's the first answer, or we can say after the dryness fraction, this is the second answer. So now after getting the turbine shaft work, the next part is to find the pump work in a similar manner. Since the power which is consumed by the pump is given by W dot P, and pump is operating between enthalpies of H3 and H4. Basically H4 is the higher value, so it is H4 minus H3 into the mass flow rate of steam. So that is the pump work formula. M dot is 10. H4 we have got from the special formula, and the value was 253.98 minus H3 value. So on calculating this, the value comes out to be 24.8. That's the third answer. So the work which is produced by the turbine is the work producing device. that is 7400 kilowatts, and the work which is consumed by the feed pump, because feed pump is a work consuming device, that is 24.8 kilowatt. Now from the values we can see that pump work is very less compared to the turbine shaft work, so many a times this pump work is neglected. It is given in the problem, but since here nothing is mentioned, we have found out the pump work, and here we have the pump work. Now work ratio and Rankine efficiencies are left, so quickly I'll find the work ratio first. In order to get the work ratio, first I need the net work. Now therefore the net work W dot net will be equal to the turbine work minus the pump work, because net work is from the turbine shaft work, we have to subtract how much is the work which is consumed by the feed pump, and therefore turbine work 7400, pump work 24.8. So that's the net work. Now after getting the net work ratio is the net work upon the turbine shaft work. So that's the fourth answer, that is the work ratio. And work ratio basically indicates out of the turbine shaft work how much is the net work. So the ratio of them is called as the work ratio. The last thing which is left is the Rankine efficiency. So therefore calculation of Rankine efficiency, for that we need the heat supplied. So therefore I can say that the amount of heat supplied in terms of kilowatt is m dot mass flow rate of steam into heat is supplied in the boiler. As we can see from the setup, the water enters the boiler at point 4 and it becomes steam at point number 1. So heat is supplied, and that heat supplied is basically H1 minus H4, and heat is rejected in the condenser. So heat supplied in the boiler and heat rejected in the condenser. Now putting the values over here. So the heat supplied is 25.46 into 10 raised to 3 kilowatts. And therefore the Rankine efficiency would be given by, see, efficiency is basically output upon input. So the output from the plant which we are getting, that is the W net after the work which is consumed by the pump has been subtracted. So W net upon heat supplied is nothing but the Rankine efficiency. Now putting the values over here, W net was 7375.2 and heat supplied 25.46 into 10 raised to 3. On calculating this, I am going to get the Rankine efficiency, and my answer is, it is 0.2896. Take the value after the decimal up to 4 places. Now multiplying this value with 100 will give me the efficiency in terms of percentage. So that is 28.96%. So that's the efficiency of this thermal power plant. And with that, the problem on the vapor cycle gets completed. At the end, if you all find my videos helpful, you all can like, share, comment and subscribe our channel and share it amongst your family and friends. Thanks for watching.